ice. So in this case, in this discussion, we're dealing with relatively wide river systems. So a typical river that has a defined channel and will develop a continuous ice cover from bank to bank over that channel. In these types of systems, the ice cover we're assuming is always floating, and the water under the cover is hydrostatic. So there may be periods where this isn't true for a brief time, but for practical purposes, this assumption is pretty reasonable for a lot of rivers. So Manning's equation is a workhorse of hydraulic modeling. It's often used to calculate steady flow conditions, basically the velocity and the stage of a river, assuming that the flow isn't changing. So that's what we mean by steady flow. And that's a reasonable assumption for short periods of time. The development of Manning's equation is a little bit outside the scope of this presentation. I'm not going to go into that. I think a lot of folks on the call are probably familiar with Manning's, but if not, it's not critical to be deeply familiar with the derivation of Manning's equation to follow along with the discussion. We're mostly going to be talking about the differences between the application of the equation in open water conditions and how that's different in ice-affected conditions. So let's step through the terms here. So in the first equation at the top here, U is the flow velocity in feet per second or meters per second, depending on your unit system. And N is the Manning's roughness coefficient, which that describes how rough a channel is. So rough channels will tend to have higher stages because of the boundary, the channel bed introduces friction, more friction than a smooth line channel, for example. And those friction losses need to be made up by higher stages, need to have higher potential energy due to the friction losses. Since N is in the denominator here under the 1, as N increases, the velocity slows down. So you can see that in the first equation. Next, we've got the hydraulic radius. That's the area of the channel divided by the wetted perimeter of the channel. That's the length of the channel bed the flow is in contact with in cross-sectional view. And that term is raised to the 2/3 power. The last term is S naught. That's the channel slope. Steeper slopes tend to produce higher velocities, but that relationship is moderated a little bit because that's under a square root term. So the first equation, we can restate that in terms of flow or discharge. That's what a lot of us communicate in. So cubic feet per second, cubic meters per second, those sort of units. And we do that simply by multiplying the velocity by the cross-sectional area of the channel. So that's where the A term comes in. That's the major difference there. So now we have a tool to estimate the velocity or the discharge in a channel, given the geometry of the channel, the roughness, and the slope of the channel. And so we can estimate that for a given stage. So the stage is kind of baked into the wetted perimeter term and the flow term. But if you think about it, as the stage rises, the terms R or A will increase. So velocity and discharge will increase with higher stages. So hopefully that makes sense. All right, so now we're going to make some changes if we're going to deal with ice and ice-affected flow. So the most significant change is now that the channel's got a lid on it. That's the yellow layer on the figure here, and it not only touches the water, but it actually goes down into the water for 92% of its thickness. So this is obviously going to change things. So we'll quickly define some terms that we're going to use from this diagram. So starting from, I'm not sure if you can see my cursor, but starting from the left here, A sub O is the area of the water in the channel from the phreatic surface, so from the blue line to the bed. D is the depth of flow, so moving to the right here, that's the depth of flow under the ice. So for the simple example, we're just going to assume a wide shallow channel where D represents the average depth. B is the channel width. A sub I over here, that's the flow under the ice, so the area from the bottom of the ice down. And then the term over on the right is just the density of ice over the density of water. That ratio is, as we discussed yesterday, 0.92 times the average ice thickness. That's the eta bar term. And then that's multiplied by the channel width. So the area from the blue line down to the bottom of the ice, or the difference between A sub naught and A sub I. So that's what that term refers to. So that's actually what this first term here is describing, this first equation here. So A sub I is the under ice flow area, and that equals the flow width times so B times D times the depth. And that equals A sub O minus the area that the submerged ice blocks the flow. So there's no flow moving through that yellow part that's submerged below the ice. There's still water up to that blue line. If you drill a hole out in the ice, there's going to be water there, but the flow is only occurring under the ice cover. So that's an important aspect to consider. So now moving down to this next equation, R sub I is the ice affected hydraulic radius. So that's A sub I, the area under the ice, the flow area under the ice over the wetted perimeter. So the major difference here is that the hydraulic radius now includes the bed and the banks, as well as the underside of the ice. In open water, the denominator would just be 1B, not 2Ds, 1B plus 2D. So this is a reasonable approximation when the channel is wide, relatively shallow, that R sub I equals D over 2. So for open water, that approximation would just go be D, would be your hydraulic radius. So we can see having a lid on the flowing water reduces the hydraulic radius by 2. So now we have an ice affected flow area in hydraulic radius terms. So now we need to come up with an ice affected roughness value. We need to modify N. So for this, we'll use what's called, we're going to call it a composite roughness value, which is a combination of both the bed roughness and the ice roughness. So to get there, we break up the flow area into 2 zones. I've got an ice region up on the top there, and then we've got a bed region, and those are influenced by their own roughness values, N sub I under the ice, and N sub B along the bed. So we're going to assume steady flow, as we mentioned. We're going to assume that the average flow velocity in both the regions are equal, and that the energy grade lines are equal in both of these zones. So we have 2 different Manning's equations for the under ice, for what's going on under the ice and along the bed, but we're going to assume that V sub I and V sub B are equal. So the overall velocity is going to work out to V sub O, which is they're all the same. So we can solve those multiple equations for a composite roughness that satisfies all of these assumptions that I just laid out, and we refer to that as the Sabin-Yves formula for composite roughness. So just through inspection, you can see that if the ice roughness is less than the bed roughness, which it often tends to be, the composite roughness will actually be smaller than the bed roughness. So that might not immediately make intuitive sense because you might think that adding ice would increase the roughness. There's more contact area, but we're actually taking that into account by modifying the hydraulic radius. So the water will be exposed to a longer perimeter of rough boundary conditions, but the overall composite roughness may be lower than what we're using for an open water condition. Okay. So these are just some examples of recommended starting values you can use for ice roughness. These come right out of the HEC RAS manual, and I think they're in the 1612 Ice Engineering Manual, the USACE manual. So you can see the roughness values are lower than what you would typically use in a stream condition, for those of you who are pretty familiar with selecting roughness values for natural channels. Again, these are starting values, so site-specific calibration will likely be necessary to dial these in. So we can use the same concepts for modeling ice jams. This isn't just restricted to stable ice covers, all this theory, but we'll get more into detail on the force balance equations and some things particular to ice jams in a later presentation. But here are some roughness values for various ice jam thicknesses and ice properties. There's some slightly more complex equations that we'll get into in a later discussion for actually selecting these values, but these are just some representative values. I won't spend too much time on this one. So now, how do we go about using this information and these modified equations for something practical? Often we'll want to estimate the stage of a river given some assumptions about the geometry and the ice conditions in a flow rate or change of flow rates. So in order to do that, we'll need to do a bit of math. So it's kind of a lot of equations on this slide, but it's not that bad. We'll start with Manning's equation again at the top left. In this form, we have the discharge equal to the roughness, the area, the hydraulic radius, and the slope terms, as we already discussed. That number 1.486, I mean, if we're paying attention, might notice that wasn't in the earlier slide. That's just a unit conversion slide, unit conversions term that we used for imperial units and non-SI units. So that's just a units correction. We do some substitutions using the definition of A sub I that we just defined, the area under the flow, under the ice, the flow area, and then the equation for R sub I that we already defined. So those all go into the equation on the top left there in substitution. And we do a little bit of algebra, which I'll skip, but you end up solving for D, which again is the depth of flow under the ice cover. So now this is the depth of flow, not the total depth of water. And again, if you drilled the hole down to the ice and measured the total depth from the top of the water surface that you observe, you'd be off by about the thickness of the ice, 92% of the ice, because that ice is floating and displacing. Well, yeah, the ice is floating. So to get H, the total depth of the water, which is often what we're interested in, we need to add 92% or 0.92 times the ice thickness. So that's in this bottom term here, H equals the ice density over the water density times eta, the ice thickness. That's that 0.92, the ice thickness term. So that's important because for a flood event, if we're thinking about water getting out of the channel and into the floodplain, it's going to be driven by this depth, not just the flow depth. So we need to think about that, and that value is usually what we're most interested in. An interesting contrast to the open water version of this is that there's this 1.32 coefficient that shows up here, well, at least in the D term as well, if you're just trying to directly compare to open water conditions. That comes from back here. We're raising the D terms to it's 2/3 plus the D term here. So you end up with 1/2 over to the 5/3 power. So that's a little bit of an exercise to the reader, I guess, to how exactly we get there. But what it shows is that there's about a 32% increase in total depth if you just put an ice lid on a flow. And so there's a lot of caveats to that. That's just sort of a rough rule of thumb. And I'll actually show an example where that's not true in the RAS section. But suffice to say, like putting a lid on the ice will tend to increase the stage. Okay. So RAS and many other hydraulic software programs which calculate 1D flow use the standard step backwater method for calculating open water stages. And with those modifications that we made to Manning's equation to account for ice, we can use it for ice-affected flow as well. So this figure shows an ice-affected channel in a profile view with flow moving from the right to the left downstream. Yeah, so this is actually, we'll talk about this slide here. So this actually shows the water moving the other direction, so sorry to flip you around, but this is moving from the left to the right downstream. So the yellow here is the ice cover, and the blue line is the water surface, and the black sloping line above everything, that's the energy grade line. That's the total energy that the water has at any given point. So this is above the water surface because the water is moving and some of the energy is stored in that flowing water. Sometimes we refer to that as the velocity head. So that's the V squared divided by 2G term. And the alpha coefficient that's along with those equations here, those account for non-uniformity of the flow in the channel, which is usually greater than 1, but we won't go into that for this discussion. We can state all this mathematically using a form of Bernoulli's equation here at the bottom. All the energy in the flow on the left side of the figure is equal to the elevation of the bed, which is equal to basically it's the elevation of the bed above some datum. So that's D2 plus the depth of the flow, D2, plus the depth of the submerged ice in the water. So that gets us up to the blue line, and then to get to the energy grade line, we add the velocity head. So we use the same summation for the downstream point, but if the velocity is the same and the depth of flow is the same, the bed slopes down, so somehow we have less energy, and the question is, where did that go? It's lost to friction along the bed and the ice interface. So that's the last term on the right, the friction head. That's lost to heat, doing work on the bed, et cetera. So that's that H sub E term over there. So we can state the energy head loss or friction head in terms of the friction slope and the distance between the sections that we're evaluating. So the friction slope can be defined using terms in Manning's equation. We here state that the friction slope equals the discharge squared over the conveyance squared. So that's the equation there on the bottom. So it's kind of an odd looking form, but it makes solving the equations easier. We haven't mentioned what conveyance is yet, though, what this K term is. So let's do that now. Okay, so conveyance, K can be expressed as follows. It may look somewhat familiar, actually. It's a good chunk of the Manning's equation that we just discussed. We're missing the square root term of that square root of the slope term. But it's a convenient way to store the channel cross-sectional geometry terms all in one variable. So we're kind of collecting those all together. So now we have the mean friction slope down is the bottom equation, and that can be estimated from the mean average of the upstream and downstream friction slopes. So it's different than the bed slope. So now we have all the pieces we need to do what's called a step backwater calculation in order to estimate the water surface elevations in an ice-affected stream channel. We'll move along here. So this is an iterative process and proceeds exactly like we would if it were an open channel without ice. For folks that are familiar with that, we'll just use the modified terms that include the effects of ice friction on the flow. So first, we need to have a defined geometry for the channel, cross-section stations and elevations, channel slope, along with the roughness and the ice thickness that we're interested in modeling the hydraulic conditions with certain ice thickness. So we also need to specify a flow rate, so the cubic feet per second of flow. And that's this is a steady state, so we're just assuming a constant flow rate. So we'll start from a cross section with a known or specified water surface elevation. So locations like a dam or at a lake that have a relatively defined stage at a given discharge work pretty well. So we'll break all this down kind of step by step because that's a lot of text to just stare at. So we start with everything we know in the top two terms, so the friction slope and the conveyance. We'll keep the friction slope for the next step. We can calculate the total energy at the boundary condition using Bernoulli's equation, and we don't have friction head for this first step because so it's just the elevation plus a known depth, plus the water in the ice, plus the velocity head. Okay, so that's that. That's all those Z terms there. Okay, so now we do the same thing at the next cross section upstream. This is the step backwater part of the process. We're moving upstream from some known downstream conditions. So we guess the depth here to start, and that might seem kind of arbitrary. But again, it's an iterative method, and we'll refine the guess later. So there's some smart, kind of efficient ways to make these guesses, but that's for another discussion. So now we have a friction slope for this section and the total energy based on our guess of the stage. So we've got, for this upstream section, we've got the friction slope S sub F and the total energy based on that guess. So now we take our friction slopes at each section and we find the mean using our mean equation here. We use this times the distance between the cross sections, that's the L term, and we find from that the friction head term, or friction head loss term, H sub E. So we take that and we add it to our downstream energy that we just calculated in the first step. And you can see that on the right side of the the equation there at the bottom. H sub E is now added on there. And so if our guess of stage upstream was good, the upstream total energy should be equal to our downstream energy plus that head loss term due to friction that we calculated. And on our first guess, we're probably going to be off, and it was just a guess. And so we'd use the error between our results to then make a better guess for the upstream stage and then repeat this whole process. So it's iterative. We specify a tolerance for how close these equations need to be until we're confident that they're accurate enough before moving upstream, so that once the error criteria is met, then we can march upstream and use what was the upstream cross section. That'll now become the downstream cross section, and we can select the next upstream cross section to continue our step backwater equations on. So for those of you familiar with standard backwater, this is pretty much exactly the same thing. We're just using these modified terms for conveyance, essentially, that have the adjusted hydraulic radius and Manning's roughness value baked into them. So I tried to cover probably a whole hydraulic engineering class lecture in under 30 minutes. So I apologize if I blew past some of you, but hopefully you got a little bit of the takeaway that we can use some of the same tools that we use for open water equations. We just make some adjustments to some of the input parameters to account for ice, and we can use that in a step backwater framework similar to how we would in an open water case. And I will leave it there for now, unless anybody has any questions.
Any questions for Chandler?